In this video, we shall look at the concepts of energy and power associated with circuits. In particular, we will look at the concept of energy and power as supplied by a battery in a circuit. This is followed by energy and power that is delivered or dissipated in a resistor. We will then discuss a few problems based on these concepts. To understand the basic concepts behind energy and power associated with the circuit, let's look at this following simple circuit. You have a battery with EMF E, and it creates current I going through the resistor with the resistance R back to the battery, the negative terminal of it. We know that current is associated with the flow of positive charge. Let's call the positive charge in this case plus Q. Let's assume that plus Q starts its journey here. So that is plus Q. And it goes through the battery from the negative terminal to the positive terminal. But note that since this is a positive charge, it will be attracted by this negative plate and being repelled by this positive plate. However, the battery provides a certain chemical energy from the chemical processes that is occurring within the battery to provide certain amount of work to this positive charge plus Q, and provides that positive Q with certain amount of potential energy, let's call it U sub Q, in order for that positive Q go through the battery from the negative terminal to the positive terminal, overcoming the natural repulsion from the positive plate. Now we know how to calculate this potential energy. It is quite simply the charge in Coulomb times the potential difference, in this case the EMF provided by the battery, E. And as we have mentioned a few minutes ago, this potential energy is provided by chemical energy due to chemical processes inside the battery. So let's call that chemical energy E sub B. So in magnitude, it is the same as Q times the EMF. So you can clearly see the conservation of energy in action here. Another concept that we have discussed some time ago is that this charge is related to this electric current I quite simply in that manner, where this T is time. So what this equation is saying, in time T, if an amount of charge of Q Coulomb passes through a certain cross-section area within that circuit, then the ratio of Q over T is quite simply the electric current in ampere. Substituting this result in here, you see that we obtain UQ, the potential energy of this charge, is quite simply IT EMF. We again note and recall the SI unit for potential energy is joules. Now by taking this potential energy and dividing it by time, you will get I times the EMF. And this is defined as power supplied by the battery. And the unit is, of course, joules per second, or quite simply watts. So this is an important result. Power supplied by the battery with EMF E is quite simply I times E, where I is the current created by the battery. Now let's see what happens as the current goes through the resistor. As the current goes through the resistor, meaning the charge, the same amount of charge plus Q, will now go through the resistor. In doing so, all the potential energy that it gained earlier from the battery will be dissipated as it goes through this resistor. And the amount of energy that gets dissipated in time T is again I times EMF. And now this term is defined as power dissipated at the resistor, or power delivered to the resistor. Now let's assume that this resistor is an ohmic material. So the potential difference across the resistor must be the same as the potential difference or the EMF provided by the battery. And that potential difference by Ohm's law is quite simply the current through the resistor times the resistance of the resistor. Now putting this in this equation, we end up with the following form for power dissipated or delivered to the resistor. It's quite simply I squared times R. We can also express power dissipated or delivered to a particular resistor in terms of potential difference or the EMF in a following manner. So since power dissipated is I times E, and we know from this equation I is the EMF over resistance, substituting the result for I, we get E over R times E, or E squared over R. So this is an alternative form for power dissipated to deliver to a given resistor, in addition to this or that. Another way to look at the result that we have just derived is by using the loop rule. Let's assume the loop is oriented in that manner. According to the sign conventions that we have explained in our previous video, the contribution to the potential difference as you travel through the battery from the negative to the positive terminal will pick up a positive E. And as you come across the resistor and you go in the same direction as the direction of the current, it will pick up a negative term for the potential difference across that resistor, and they should sum up to 0. Now rearranging this equation, you get that. Now let's multiply both sides of this equation with I, E on the left, and the right side will become I squared R. So you see power delivered by the battery equals power dissipated or delivered to the resistor, which is the result that we have obtained a few minutes ago. And you see how loop rule is consistent with conservation of energy law. Let's look at the following problem. In the circuit below, find the rate of conversion of chemical energy to electrical energy within the battery, the rate of dissipation of electrical energy in the battery, and rate of dissipation of electrical energy in the 5 ohm resistor. So before we proceed, we need to determine the current I. What is the current I? We can do that by using the loop rule. Now remember, this 1 ohm resistance is the internal resistance of this battery with EMF 12 volts. So let's write down the loop rule. As you go through the battery from the negative terminal to the positive terminal, it will pick up a positive term for the potential difference, so it's positive 12. Then you go across the internal resistor of the battery in the same direction as the direction of the current I. So that's going to give you a negative term for the potential difference across that little resistor. And that term is I times resistance 1 ohm. Next you go across the 5 ohm resistor, again in the same direction as the direction of the current I. And that will give you another negative term for the potential difference across that 5 ohm resistor, and that is I times 5. And they all should sum up to 0. Immediately, you can figure out what I is. I is quite simply 12 over 6, which is 2 ampere. And now you can answer the question. Part A is the rate of conversion of chemical energy to the electrical energy within the battery. So that is to say, what is the amount of power supplied by this 12 volt battery? Now that is quite simply the current through the battery times the EMF of the battery. Now we have determined the current I to be 2 and the EMF is 12. So together you get 24 watts for part A. Now for part B, the rate of dissipation of electrical energy in the battery. Since the resistor 1 ohm here is within that battery, so the rate of dissipation of electrical energy in the battery is quite simply the power delivered to this 1 ohm resistor. And the power delivered to 1 ohm resistor is I squared times that resistance of that 1 ohm resistor, which is 1 ohm. And since I is 2 ampere, so 2 squared, and that's going to be 4 watts. Now finally, part C. Part C says the rate of dissipation of energy in the 5 ohm resistor. So that's this resistor right there. So the rate of dissipation of electrical energy is quite simply the power delivered or dissipated in that 5 ohm resistor. So the current through it is I, which is 2 ampere, so 2 squared, times the resistance, which is 5 ohm. So 2 squared times 5, and that is 20 watts. As a check, you see that this 20 plus 4 should be the same as the power supplied by the battery, which is 24. And that solves the problem. Problem 2. A circuit with 12-volt battery supplies current to a 1000 ohm resistor. What is the current in the resistor? And find the power delivered to the resistor and the energy delivered to the resistor in 30 seconds. So since that is just one battery and one resistor, the circuit is very simple, like that. So this is a 1000 ohm resistor, and this is a battery with EMF 12 volts. So the current I in that direction is quite simply the 12 volt divided by 1000 ohms, and that's going to be 0.012 ampere. Now, power delivered to the resistor is quite simply the current that we have computed in part A times the resistance of that resistor. So the current is 0.012 ampere, square that. The resistance is 1000 ohms, and that's going to give you 0.144 watts. Part C, the energy delivered. Now energy is power times the time interval. The power is 0.144 and the time interval is 30 seconds, so times 30, and you will get 4.32 joules for the energy delivered to the resistor in 30 seconds. Problem 3. Find the power delivered to each resistor, shown below, and also the power supplied by the battery. Note, the battery's EMF is 18 volts. So this 18 volt must also be the same as the potential difference across this 3 ohm resistor, the 6 ohm resistor, and the 6 ohm resistor, because all these resistors are connected parallel to each other, and also their terminals are connected to the terminals of the battery directly. So the power delivered to the 3 ohm resistor is quite simply the potential difference across that 3 ohm resistor, which is in this case is 18, squared over the resistance, which is 3 ohms. Remember the alternative expression for power delivered to a resistor, which is the potential difference across that resistor over the resistance of that resistor. So in this case, it's 108 watts. Next, similarly, power delivered to the 6 ohm resistor, that is this one right there, is 18 squared over 6, which is 54 watts. Now, power delivered to that 6 ohm resistor, using similar equation, is quite simply, again, the potential difference across that, which is 18 volt, over the resistance of that resistor, which is 6, and you will get 54 watts again. And finally, power supplied by the battery. The power supplied by this 18 volt battery must be the same as power dissipated or delivered to this resistor, plus the power delivered to this resistor, plus the power delivered to that resistor, which in this case, 108 plus 54 plus 54, and that's going to give you 216 watts. And that solves the problem. Thank you for watching.